Okay, you guys, let's start section 4.3. Here we go. So the intermediate value theorem says that given p is a polynomial with real coefficients, if p of a and p of b have opposite signs, so p of a is positive, p of b is negative, that kind of thing, then there's at least one number c between those a and b's that's a zero. So think of a cubic function that looks like this. So this value is negative when you evaluate it, this one's positive. Somewhere between here and here, there must be a zero because we cross the x-axis. That's all that's saying. So what I would do if I were you on this problem, use the intermediate value theorem to show that there's at least one zero. I would put that in your y equals x cubed minus 9x plus 6. And I would go to your table, okay? And then we're going to evaluate at each of these spots. We're going to take p of negative 4, one boundary. And when I evaluate at negative 4, I get negative 22. I'm just looking at my table now, okay? P of 3, as I evaluate there, is 6. And since one value is negative and one value is positive, they have different signs. There is definitely a 0 between negative 4 and 3, okay? Similarly here, well, we know p of negative 4 is already negative 22. We've already evaluated that. Negative 3 is also 6. So one's positive, one's negative. Got to be a 0 in between. So this is a yes as well. Down here, p of 0 is negative 4. And p of 1 is negative 2. P of 0, I read wrong, is 6. So one's positive, one's negative. We definitely have a 0 somewhere between 0 and 1. Okay? So that's all they're asking you for on that type of problem. The rational zeros theorem. Given p is a polynomial with integer coefficients, and p divided by q is a rational number in lowest terms, so 2/3, 3/4, that kind of thing. If p divided by q is a 0 of p, then p must be a factor of the constant term and q must be a factor of the leading coefficient. They're going to use this theorem to ask you to list all the possible rational zeros. Where we're headed with this is we're going to be trying to find all of the zeros, and we're going to try to make our life a little bit easier by finding the rational ones first, which are easier than irrational numbers. Okay? So here's all they're asking. List all the possible rational zeros of p. Okay? It's always going to be plus or minus. And then the constant term is negative 24. And so let's just list the factors. What are the numbers that go into negative 24 evenly? 1, 2, 3, 4, 6, 8, 12, and 24. So those are all of the possible numerators of that fraction. And then on the bottom are the factors of the leading coefficient, which is 3, 1 or 3. So the rational numbers that could be zeros of this, 1 over 1, 1 over 3, plus or minus 2 over 1, 2 over 3, etc. And so as you're looking at your graph and you're thinking of values to try, I would start with the rational ones because they're a lot easier to check. Okay? Another way to help us through this, we're trying to get, not shortcuts necessarily, but ways to help us determine quicker which ones are zeros. If the sum of all the coefficients is 0, so if you add up all the numbers out in front and you get 0, then 1 is a root, and you can factor out an x minus 1. Okay? And if you change the signs of all of the odd terms, or odd degrees, so x to the third, x to the fifth, etc., and then the sum of the coefficients is 1, well then negative 1 is a 0. And we'll use that a little bit. These are just tools to help you get through these a little bit quicker. So find all rational zeros of that function and use them to write the function in completely factored form. Then use the factored form to name the zeros of p. Okay, so let's use what we learned on the previous slide for a second. Let's add up these coefficients. 3 plus negative 1 is 2, plus negative 14 is negative 12, plus 4 is negative 8, plus 8 is 0. And since all of the coefficients add up to 0, I know 1 is a factor. And so I'm going to use some synthetic division here to break this down a little bit. So 3, negative 1, negative 14, 4, and 8. And because of what we learned on the previous slide, we believe that 1 is a 0, so we're going to put a 1 out in front. Now, if this is true, I should get 0 for a remainder, remember. Okay, so I bring down the 3, multiply, 3 times 1 is 3, add these up and I get 2. 2 times 1 is 2. Add those two up and I get negative 12. Negative 12 times 1 is negative 12. Negative 12 plus 4 is negative 8. Negative 8 times 1 is negative 8. And sure enough, those add up to 0. Okay? What am I left with though? So this means I've got an x minus 1. We know that that's a factor. And I've got 3x squared, or 3x to the third plus 2x squared minus 12x minus 8 left. Okay? Can we factor that more? Okay? What I would do if I were you guys, okay, is I would put this in your y equals and graph it. Okay? We already checked 1. We were pretty sure that 1 was a 0 and we tried it and yep, that definitely worked. But as I'm looking at my graph, I'm interested in where it crosses the x-axis because those are zeros. So I'm looking at my graph and I think 2 is also a 0. It looks like it on my graph. The only way to know that for certain is to break it down. So I'm going to use synthetic division again, and I'm going to test 2. Okay? If it works, I should get a 0 for a remainder. So bring the 3 down, multiply, I get 6, add up, I get 8. 8 times 2 is 16. Add those two up, I get 4. 4 times 2 is 8. Sure enough, 2 is also a 0. Now I'm left with 3x squared plus 8x plus 4. Okay? It also looks to me that negative 2 is a 0. It looks like I crossed the x-axis at negative 2. So I'm going to do this one more time. I'm going to try negative 2. Okay? So bring the 3 down. 3 times negative 2 is negative 6. Negative 6 plus 8 is 2. 2 times negative 2 is negative 4. Sure enough, that's also a 0. Now I'm left with 3x plus 2, which is pretty straightforward. So it says find all rational zeros and then use the factored form. So let's write this in the factored form. 1 is a 0, so x minus 1 is a factor. 2 is a 0, so x minus 2 is a factor. Negative 2 is a 0, so x plus 2 is a factor. And then I'm left with 3x plus 2 at the bottom. So that's completely factored form for this. And then it says name all the zeros. Okay? So I'm going to put zeros equal. Well, we know that 1, 2, negative 2 is a 0. And what's going to make that 0? Negative 2/3. And so I've got a way to help me through this. I think the most efficient way, guys, is to graph it. Look to see where it crosses the x-axis, and if it crosses at nice values, use synthetic division to break it down. And if you get to the point where you've got a quadratic worst case scenario, you could factor it, use the quadratic formula, something like that, to find your other zeros if they weren't nice. Okay? So that's how I would tackle that problem. All right, find all the zeros of this function. You know what? The same thing, you guys. I know that the possible rational zeros are the factors of 12, which is limiting, over the factors of 1. So I'm going to just go in here, and I would ask that you do the same. Grab your calculator, type into your y equals x to the 5th minus 3x to the 4th minus 3x to the 3rd plus 13x squared minus 12. Okay? And then just graph it in your negative 10 to 10 window, because I know the factors have to be, if they're rational, factors of 12. Okay? And I'm looking at my graph, and it looks like I cross in 3 places. Okay? So I'm going to set up for synthetic division. I have 1x to the 5th, negative 3x to the 4th, negative 3x to the 3rd, 13x squared, 0 x's. I need a placeholder for that, and be careful. And then minus 12, okay? So, I'm looking at my graph, and I clearly cross at -1. If you're not 100% sure, you can check your zero, your table as well. So I'm gonna go in here and I'm gonna test -1. So, okay, again, multiplying, add these up, I get 1. Multiply, I get -1, that's a 12. Multiply, I get -12. Multiply, and I get +12. That's clearly a 0. Now, I went from a 5th degree to a 4th degree, so I've helped myself a little bit, but I haven't completely solved the situation here. So I've got more to do. Okay, so we're going to try 2 next. And again, I'm picking 2 just because when I look at my x-axis, when I look at my graph, it looks like I crossed the x-axis at that point. So I'm going to put a 2 out in front. Okay, add these up and I get -2. Multiply, -4. Add these up, I get -3. Multiply, I get -6. Add these up, I get 6. Multiply, I get 12. As we expected, we got 0 again. But now I'm down to a 3rd degree polynomial, which potentially I could factor if it grouped right, okay? The interesting part, and we're going to talk about repeated zeros here, is we might have a repeated 0 in this situation. I come up and there's just a little inflection point. It changes, it doesn't quite change directions, it looks like it wants to, and then goes back up. So I might try 2 again, okay? And this would simply mean I just have a repeated 0. Let's see what happens. So I put a 1 out in front, multiply, add up, multiply, get 0, add up, multiply, get -6, okay? And just because it worked once does not mean it will work again. It just happened to work again here, okay? So we're supposed to find all of the zeros. Let's talk about this factored form right now. So -1 is a 0, so I know I've got x plus 1. 2 is a 0 twice. What that really means is I've got x minus 2 listed twice. And I went from 5th degree to 4th degree to 3rd degree down to 2nd degree. So this is x squared plus 0x minus 3. So let's think about what our zeros are here, you guys. Okay, clearly -1 and 2 are zeros. If you set that equal to 0, you'd add 3 and you get x squared equals 3, and you'd have to take the square root. Okay, and so it's going to be plus or minus the square root of 3. Okay? Those are a little harder to see on the graph, but is what it is. Okay, so when asked to find all the zeros, graph it, look to see where it crosses the x-axis, and then just try these until you can break it down to something that you can solve easier, okay? All right, Descartes' rule of signs, we're trying to determine how many positive and negative zeros we have. So the number of positive real zeros is equal to the number of variations in signs. So you just look through the polynomial and see when you change signs. So if you go from positive to negative from term to term, or is an even number less, meaning if there are 4 sign changes, it could be 4 or 2 or 0. You just keep subtracting 2 until you run out, okay? And the number of negative zeros is either equal to the number of variations in the sign of p of negative x. You put a negative x in, see how many times you change sign, and that's how many negatives you could have, or less than that by an even number, so 5 or 3 or 1, that kind of thing, okay? So we're going to take a look at an example here. Use the rational zeros theorem to list all the possible rational zeros. Okay. Well, I'm going to put a up here. The constant term is -16, so the factors of 16 are 1, 2, 4, 8, and 16. And then the leading coefficient is just a 1. Okay? So if there's going to be rational zeros, it's going to be plus or minus 1, 2, 4, 8, or 16. So if I'm checking, that's what I'm looking for. B, applied Descartes' rule of signs to count the number positive, the number of negative real numbers. Okay, so let's look at positive for a second. So x to the fourth is positive, and that's positive, and that's positive. So we haven't changed signs yet, but positive to negative here we did. So there's one sign change here from a positive 12x squared to a negative 4x. But then I go negative to negative. So there's only one positive possible value because there's only one sign change in there. Okay? Let's look at p of negative x to help us determine how many negative ones there could be. So what if I put a negative into an even powered function, a negative raised to the fourth is going to be positive again. This will become negative because a negative raised to the third will change sign. So minus 7x cubed. That will stay the same because it's even. That will change signs there. And there's no x there. So let's count those. So positive to negative, 1. Negative to positive, 2. Positive to positive, nope. Positive to negative, that's 3. So there's 3, and then less than that by an even number, or 1. Okay? And so use this information in the tools of this section to find all the real zeros of p. Okay, so now we're going to do what we did on the previous slide. So I would suggest you go into your y equals, and we're going to put that function in there, x to the fourth plus 7x to the third plus 12x squared minus 4x and then minus 16. And we're going to graph it. Okay? And I'm going to go on to the next slide to just give me a blank slide to work with here. Okay? So I have 1x to the fourth, 7x to the third, 12x to the second, negative 4x, and negative 16. Okay? Looking at my graph, it looks like I crossed the x-axis at negative 4, so I'm going to test that one. And negative 4 was one of our possible rational numbers because it was a factor of 16. And there was 1 or 3 negatives, so that made sense. So bring the 1 down. Negative 4 times 1 is negative 4. Add these up, I get 3. Multiply, I get negative 12. Add them up, I get 0. Negative 4 times negative 4 is 16. Sure enough, that was a 0. Okay? It looks to me like we cross at 1 for sure. 1 is a factor of 16, so that makes sense. Bring down the 1, add them up, multiply, add them up, multiply. Okay? Certainly, now I'm down to a quadratic. Okay? It also looks to me like I come up and I touch the x-axis at negative 2. So I'm going to try negative 2. Okay? And so then let's look at what this factors to. So if negative 4 is a 0, I have x plus 4 and x minus 1. This would be x plus 2. That's also x plus 2, so that's going to be quantity squared. So if I want to list my zeros, we got negative 4, 1, and 2. And negative 2, sorry. Okay? So think of what we said on the previous page. We said there could be one positive 0, and there could be 1 or 3 negative ones. Well, how come I listed 2? Well, that negative 2 is a repeated 0. There's 2 of them that are negative 2, and 1 that's negative 4, so there's 3 negative ones, actually. Okay? So that's how I would tackle that type of problem. All right, upper and lower bounds. So we're trying to determine if a number, so if 5 is an upper bound, that means there's no zeros bigger than 5, okay? And if 0 is a lower bound, for instance, there'd be no zeros to the left of it. And the test for that is, if you divide by a number using synthetic division, and the bottom row is all 0 or positive numbers, it's an upper bound. If the bottom row is all alternating between positive and negative, then it's a lower bound. Okay, so if we need to do that, that's all it is. In the fundamental theorem of algebra, every complex polynomial has at least one complex zero. Okay. As a matter of fact, if the polynomial is degree n, there are n complex zeros. Okay. And remember, all of the real numbers are a subset of the complex numbers. Okay. Corollary polynomial function of degree n has exactly n zeros. That's what we're talking about there. Okay. Including repeated in the complex number system. So rewrite that as a product of linear factors. Now, this particular one happens to factor. It's in quadratic form because the fourth power is twice as much as the second power. So let's ask ourselves, can you think of numbers that multiply to 9 and subtract to 8? Sure. Okay, so we've got x squared and x squared, 9 and 1. I need a negative 8, so we're going to go like this. Okay? I can factor this a little bit more. This is x minus 3 and x plus 3. It's a difference of squares. X squared plus 1, so we want it as a product of linear factors and find its zeros. What's going to make that 0, you guys? Because it's plus 1, it's a complex 0. If I set that equal to 0, I'd have to take the square root of negative 1, which is I. Okay, so technically if I wanted to factor it, it's going to look like that. So my zeros are plus or minus 3 and plus or minus I. Now graphically, when you graph this thing, you will clearly see it cross the x-axis at plus or minus 3. But because these two are imaginary, that doesn't do anything for us graphically. You won't see that on your graph. You won't see that in your table anywhere. The only way to get that is to do some algebra. Okay, so I think factoring was maybe the most efficient way for us to do this one. Okay? Very similar here, rewrite that as a product of linear factors and find its zeros. If I can factor it, I will, because I think it's quicker. I've got 4 terms, so if I can group this, I'm going to try. These first 2 terms I can take an x squared out of. If I do, I'm left with x plus 2. Okay? The next 2 terms I can take a negative 4 out of, and I'm left with x plus 2. And because I got the same thing in parentheses, I can factor out an x plus 2 from those terms. Okay? If I factor that x plus 2 out, I'm left with x squared minus 4. So I've got x plus 2. And then this is a difference of squares. This is going to factor to x minus 2, x plus 2. Okay? And I want, do you notice how negative 2 is a repeated 0 there, you guys? So I'm supposed to find its zeros. Well, they're really just plus or minus 2. The negative 2 is repeated. So there's 3 zeros, 3 complex zeros like that corollary said. One of them is repeated. Okay? Multiplicity of zeros, we already saw this a little bit. If p is a polynomial function and x minus c occurs as a factor of p exactly m times, so x minus c to the 5th, then c has zeros of multiplicity m, so that would have been multiplicity 5. Factor the given function completely, writing repeated factors in exponential form, and I'll show you what I mean by that. Then state the multiplicity of each zero. Okay, so let's factor if we can. This is potentially a perfect square trinomial. That's a perfect square and that's a perfect square. So I've got x plus 4. If I multiply these 2 together, x times 4, and double it, I get the middle term. So that's quantity squared. Okay. This term, what numbers multiply to 20 and subtract to 1? 4 and 5. I need a negative 1, so we're going to go like this. And then I've got an x minus 5. Okay, so I've got a lot of the same terms up here. So it looks like I've got x plus 4 twice, 3 times. So I'm going to go x plus 4 to the 3rd power. And then I've got x minus 5 listed twice. That's going to be quantity squared. So that would be factored with factors in exponential form. And then I'm supposed to state the multiplicity of each zero. So the zeros are negative 4, multiplicity 3, and 5, multiplicity 2. Multiplicity 3 here because it's to the 3rd power, multiplicity 2 here because it's to the 2nd power. That's what they're asking you to do. Okay, a couple more examples, and then we'll get you going. If p is a polynomial with real coefficients, complex zeros must occur in conjugate pairs. So if 3 plus I is a 0, then 3 minus I is also a 0. They come in pairs. That's what they're saying. So, a real polynomial p of degree 3 has zeros of -1 and 2 plus I squared to 3. Find the polynomial. Okay, so if -1 is a 0, then x plus 1 is the factor. If I put a -1 in, I get a 0. If 2 plus I squared to 3 is 0, then I'm going to go x minus 2 plus I squared to 3. Okay? And its conjugate pair has to also be a 0 from the previous slide. So 2 minus I square root of 3 is in there as well. Okay? So I want you to think of it this way though. This part gets a little complicated when I multiply it out, so I want you to rewrite this a little bit. Think of this one as x minus 2, and then distribute that minus I square root of 3. And x minus 2 plus I squared root of 3. And the reason I rewrite it that way is because this is now in the form a minus b, a plus b. And if you recall that a minus b times a plus b is just a squared minus b squared, that's going to make our life a little bit easier. Okay, so I've got the x plus 1. And if I think of a squared minus b squared, I've got a, which is x minus 2 squared, minus b squared. Well, if I take I squared to 3 and square it, I get 3i squared. Since I squared is -1, I get -3 minus the -3 is plus 3. Okay? So then I have to work this out just a little bit more. Okay? So, different colors so we can see this a little bit better. So I'm going to take and square that. I'm going to leave the x plus 1. X minus 2 squared is x squared minus 4x plus 4, right? But plus 4 plus that 3 is plus 7. And I'm almost done, you guys. So my final answer here, we're going to come up with some polynomial, let's call it f of x. I have to distribute the x to all 3 of those and the 1 to all 3 of those. And I'm going to save you a little bit of time. I think you guys can take your time to do that. I should get x cubed minus 3x squared plus 3x plus 7. And again, they've worked this out in the book too if you want to look at it. But that's how I'm going to have to do this. So a couple things to be careful with. You had 2 plus I squared to 3. Its complex conjugate pair, 2 minus I squared to 3, had to also be listed as a 0. So there had to be at least 3 zeros. Okay? And then just take a look again at how I rewrote that. X minus 2 plus I squared to 3 and x minus 2 minus I squared to 3, so that I can multiply that out as a squared minus b squared. It'll make your life a little bit easier. If this one seems confusing when you're trying it in the homework, come back and look at the video a couple of times and check out how to do it. Okay? Last example here, I believe. So I've got this polynomial. Use the rational zeros theorem to list all the possible rational zeros. Okay? We can do this. Plus or minus factors of 6, and then over the factors of 2. So if I'm going to have a rational zero, it's going to be plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 1, plus or minus 3, plus or minus 3/2, etc. Okay? Apply Descartes' rule to count the number of possible positive, negative, and complex zeros. So I know there's a total of 5 complex zeros. So positive, let's count the sign changes. We went from positive to negative here, so that's 1. Negative to positive here, that's 2. Positive to positive, no. Positive to negative, that's 3, and negative to positive is 4. And since it's less than that by an even number, we could have 4 or 2 or 0 positives. Okay? Negatives. Let's look at p of negative x for a second here. Okay? So that's going to be negative 2x to the 5th. The even powered ones will stay the same, and the odd powered ones will change signs ultimately, you guys. Okay? So that's p of negative x. Let's count our sign changes here. So negative to a negative, nope, to a negative, nope, to a positive, there's 1, but then they're all positive after that. So there's only one possible negative one. So complex, well, if there were 4 positive and 1 negative, that would be 5 total. So there could be 0. If there were 2 positive and 1 negative, that would give me 3, meaning I'd need 2 more complex to get to 5. If there were 0 positive and 1 negative, that only brings me to 1, which means I could have 4 complex zeros as well. So those are my possibilities for that. And then I want to use this information in the tools of this section to find all of the zeros. Okay, we're going to go back to how we did this before. So I would go into your y equals, you guys, put in this function, 2x to the 5th minus 5x to the 4th plus x to the 3rd plus x squared minus x plus 6, okay? And I'm going to do a lot of my work on the next screen here. Well, I'm going to go back. Okay, so let's take a look at that for a second. I'm going to erase what I have up here. And I'm looking at my graph, and it looks to me like I cross in 3 places. Okay, so we're gonna try to break it down to at least that spot. Okay, so I'm gonna do some synthetic division. I've got 2x to the 5th, negative 5x to the 4th, 1x to the 3rd, 1x squared, negative 1x, and 6. Okay. And looking at my graph, and you guys can look at the same, it looks to me like I cross at negative 1. So I'm going to try that as one of them, okay? Bring down the 2, multiply, 8, negative 1 is negative 8. Add those up and I get negative 7. Multiply, I get 7. That's going to give me 6. So as I expected, that was a 0, okay? It looks like I cross at 2 as well, okay? So let's try 2. So 2, 4, add these up, I get negative 3, negative 6, 2, 4, negative 3, negative 6. So certainly that was a 0 as well. Now I'm down to a, 4/3 third degree, okay? And it looks like I cross at one more place. And this one's a little bit of a decimal, so I'm gonna have the calculator help me a little bit. It looks like 1.5. So I'm going to try, I apologize that I'm getting in the way here, 3 halves, okay? So I bring down the 2, 3 halves times 2 is 3, add them up I get a 0, of course 0, 2, 6 halves is 3, okay? So as I expected, I got 0 for that one as well from the calculator. So let's think about what's left here, you guys. I've got negative 1, so that's x plus 1 is a factor. I've got a 2, x minus 2 is a factor. I've got 3 halves. So I've really got 2x minus 3 as a factor. And then this is left with 2x squared plus 2. Okay? All the zeros. So let's think about this. Negative 1, clearly, 2, and 3 halves. And we tested all of those up here. But these ones, 2x squared plus 2, subtract 2 and divide by 1, and I'm going to get x squared equals negative 1. Well, that means plus or minus I is a 0 as well. And so go back to what we talked about. We've got 2 positives, 1 negative, and 2 imaginary, or 2 complex. It seems to match what we're talking about. And all of these are these rational ones, right? Negative 1 is right here, 2 over 1 is here, 3 over 2 is here. Those are all possibilities, so that seems to make sense, okay? All right, you guys, so take a look at the assignment that's going to be posted under Google Classroom and give this a shot.